Hi, welcome to today's class. In today's class, we are discussing about inference for model parameters when you fit a simple linear regression. Now, inference here means we want to test whether the parameters that we have estimated, that is the constant and the slope, are actually representative of the population. Do they give evidence that the model that we have estimated is significant? Do they indicate that the slope and the constant are important in our model? We shall continue. This is how we shall continue with our discussion. First, we are going to look at the confidence intervals for the slope and the constant, and then thereafter we look at the testing the significance of the whole model, and then we look at how we can test the significance of the slope and the constant separately using hypotheses. So let's start our discussion. We start by looking at the confidence interval for the slope and the constant. Now let's consider the simple linear regression model, which is given as follows here, where you have got y is determined by the linear model and then the error term. This part of the model is the one that we estimate. So one of our key concerns after fitting the simple linear regression model is whether the slope, this one, beta 1, or the constant are indeed equal to 0 or not. If these two are equal to 0, it means that the model is actually not significant. It means that then whenever x changes, y does not change. So we don't need this part of the model. That's what it would mean. But we'll be seeing how we do that. Now, one of the things that we need to think about is the consequence of having the slope being equal to 0. If the slope is equal to 0, for example, it means that when x changes by 1 unit, y changes by 0 units, which means y does not change. And therefore, x has no effect on y. So there is no effect. And if the constant is equal to 0, it means in the absence of x, there is nothing that is explained by the constant. So all the variance of y is explained by the error term. So if the slope is equal to 0, it means that a unit change in x will lead to 0 change units in y, and therefore it implies the predictor is not significant. Now, the estimates of beta naught and beta 1, which are given by B1, the OL estimates B1 and B0 and B1, are obtained from sample. Other samples drawn from the same population will yield different estimates. Each sample is drawn from the same population, but each sample will give you a different value or different estimates for B1, B0, and B1. The implication of this is that one sample can give us estimates of the slope that are equal to 0, and another sample may give us estimates of the slope that are not equal to 0, meaning that one sample indicates the variable x is not useful, and another sample from the same population indicates that x is useful. This is a contradiction and is caused by the sampling error because it depends with which sample that we have taken. So instead of depending on the point estimates of the constant and the slope, we can then prefer to rely on interval estimate. And an interval estimate is an interval that we construct, which we are a certain percent confident sure that the true value will lie within. And we normally call such interval estimates the confidence interval. Okay, the level of the confidence interval is determined by the level of significance alpha, as we saw with the case of the correlation coefficient. And the confidence interval is therefore calculated based on the standard error of that particular estimator. So now I want us to see how we construct the confidence interval of the slope. The proof of how this is obtained is beyond the scope of this course, but it can be shown through some mathematical procedure that the standard error of the slope is given by this formula. So you have got the standard error of the slope B1 is given by the square root of the sum of the squared deviations of the estimated value from the true value, and divided by n minus 2 times the sum of the values of the predictor and their deviation from their mean, and you square that. That gives you the standard error. And y hat here, this one here, is what we obtain when we substitute values of x in this equation. And we will see how we do that with an example. So now, when you take the sum of squares due to the error and you divide by n minus 2, that gives you what we call the standard error of the residuals. It is this sum here, this value divided by this. So you computed this with this one. The difference between the observed value and the estimated value is known as the E, that is the residual. So this is the sum. You can write this one as sum of E, the error squared. And then you are dividing this one by n minus 2. So this one is known as the standard error of the residuals, and we use it in computing the confidence interval of the slope. Now, given the standard error of the slope, we can compute the 101 minus alpha 100% confidence interval for the slope to be equal to this formula. Now, the proof of the formula is not important, but you've got to remember this is the OLS estimate of the slope, and this is the standard error of the slope. This one here is the tabulated t-value at alpha level of significance and n minus 2 degrees of freedom. We normally use the 95% confidence interval, in which case alpha will be equal to 5%. When we take this, when we separate the signs here, we have the lower limit, this one, which is given by B1 minus the table value times the standard error, and the upper limit is obtained by B1 plus the table value times the standard error. And this is what we have in graphically. So if you look at this, you have got the lower limit and you've got the upper limit. So whenever now we expect that 101 minus alpha percent of the time, our true value will lie inside here. Now, to determine if the slope is significantly different from 0, we look at the lower limit and we look at the upper limit. If 0 lies somewhere in between them, that is 0 is somewhere here or anywhere within this interval, then we conclude that the slope is not significantly different from 0. And if the slope is not significantly different from 0, then the predictor variable x is not going to be useful for predicting the response y. Let's now consider the confidence interval for the constant, that is beta naught, this one here. And the confidence interval for the constant, we want to find out if the constant is different from 0. Again, we will not rely on the point estimate, but we will have to construct a confidence interval. And so we construct the 95% confidence, the 1 minus alpha percent confidence interval, which will be based by computing the standard error of the constant. Now, the standard error of the constant is obtained using this formula. Now, again, the proof is beyond our scope. The S here is the standard error of the residuals, which we have done in the previous slide. This is the sum of the squared values of the predictor, and this is the variance of the predictor variable, and this is the sample size. So now you use this formula to compute the standard error. Now, having obtained the standard error of the constant, we can now compute the confidence interval, that is the 1 minus alpha percent confidence interval for the slope, which is given by this formula. Again, this is the ordinary least squares estimate of the slope, and this is the standard error of the slope. We have seen in the previous slide how you compute this one, and this one you obtain from the table values. That we did see how you get that one from the t tables. Now, the lower limit, therefore, is going to be when you take the minus sign, and the upper limit is when you take the plus sign. Now, if 0 lies in between the lower limit and the upper limit, then we conclude that the constant is not significantly different from 0, and therefore we don't need the constant in the model since it is not useful. Let us now move on and look at an example. This is the example we are looking at. Consider the relationship between the GDP in $1 billion and the 3-month treasury bill rate, TB rate, which is given in percentage. We will show you the data below. Now, number one, estimate the simple linear regression model with TB rate as the response variable. Then construct the 95% confidence interval for the slope, and then answer the question whether there is any evidence that the GDP is statistically useful in predicting the 3-month treasury bill rate, and also if the constant is statistically useful. Let's see how we deal with this. The first step is for us to compute the ordinary least square estimates for the slope and for the constant. Now, the slope, we use this formula here, and the constant, we use this formula. So from here, we will see that we need the sum of x, y, this one here, multiply the x values and the y values, then you sum. We will need to square the values of x, and then we sum them. And we'll need to sum the values of x and the values of y. All this we will input in this formula. And then we will need the mean of y and the mean of x so that we can compute the estimate of the slope. This is the data that we are provided with. The GDP is our x, and you have got the TB rate as our y. So now we first of all estimate the slope, and we know that this is the formula that gives us the slope. So first of all, we go to multiply x by y, then we sum. So doing that, this is what we get. So we are multiplying the values of x, this one times this, you get this. This times this, you get this. Then you multiply all of them all the way down up to here, and then you sum. So now when you sum, the next thing that we need is the sum of x squared. So we square the values of x. These are the values of x. Square 2795.6 you get this value. Square 31.3, and you'll get this. Square 3259.2, and you get this. You can get all these values using your calculator. Then add all of them. Okay, and when you add them, this is the result that you get. So these are the sum. This is the sum for x, and this is the sum for y, and this is the sum for xy, and the sum for x squared. And those one we will now input these results in this formula to be able to compute. But we will first of all compute the mean, and when we input the results, sorry, we don't compute the mean. When we input these results in the formula, our n is equal to 19. You add all this, so you've got 19, that is n, and then you've got this sum here, which is down here, which is the one you got here, and this one is the sum of x, which is here, and the sum of y, which is this one here, and we had obtained it from here. So you are substituting those values, and this one too, you get them from the table from down here, and you substitute all of them, and then solving this using a calculator, the result we get is that B1 is equal to negative 0.0013, and now we can go ahead and get B0, and B0 is going to be given by getting the mean of y minus B1 times the mean of x. Now the mean of y is simply the sum of values of y, which is this one here, 132.62. You divide by 19. The mean of x is this value, 104,738.8 divided by 19. So if we do that, this is what we get. We have substituted, and then we get our answer is 14.15. So we have estimated the value of the B0, and we have estimated the B1. So the next thing now is we move ahead and compute the required standard errors. So this is our estimated model, by the way. So after we estimate, this is our estimated standard model. So let's move on. So to compute the 101 minus alpha % confidence interval for the slope, we found that this is going to be the formula. So we need to get the value of B1, which we have already computed. Now we need to compute the standard error. This one we get from the tables. We'll see how you go about it to get that. Now at 95% critical value, at 95%, the critical value that we need is going to be T1 minus alpha over 2, which is equal to 0.975, and this gives us 2.11. I'll show you just here in slide how you get that. Okay, so here we have got our alpha is equal to 0.05. That is 1 minus 0.95, because we are using the 95% confidence interval. So now when you alpha over 2 is going to be 0.05, and then you have got 1 minus alpha over 2 is 1 minus 0.025, which is equal to 0.975, and so your n is 19. So your t, you come to the t table to read off the t, and the t table, you will notice that down the column you have got the degrees of freedom, and then across the top row you have got the various levels, 50%, 75, 90. This is 0.975 is right here, and then you drop down to where there is 17, and you could move across with 17, and now read off the value that is coming out there, and this is 2.11. So our tabulated t value, as I had shown you in the previous slide, is going to be 2.11. Now we need to compute the standard errors. So let's see how we compute the standard error. So this is the formula for the standard error. So to compute this, we need this sum, and we need this one. First of all, we need to compute the estimated values of y using this equation. Let's see in the next slide what happens. So this is our data. To compute this value here, what we do, we substitute in the equation. That is our formula. So we want to compute the estimate. For example, to get this value here, 10.5, you come to this equation, and replace x by 27.595.6, which is this one. Then solve 14.5 minus this times this, you get 10.52, which is what is here. Now to get this one, you will come here and get y2 is equal to 14.15 minus 0.0013 times 31.3, which is going to give you 10.08. And you repeat that all the way for each of the values until up to the bottom. And now from there, after we have computed the estimated values of y, we can now get the difference between the observed values of y, which are these ones here, the TB rate, and the estimated values of y, which are these ones here in this column here. So we now look through, we now take, for example, 11.506 minus 10.52, then whatever you get the difference, you square, you get 0.98. Take 14.029 minus 10.08, then you square, you get 15.6. 10.686 minus 9.91, and then you square. So this is the value that you get. So you repeat that and all the way down, and so that you get the sum. Now you add all this to get the sum of these values here. Now and that sum is going to be 55.73, which is the one that you are seeing here. It is the sum of the squared deviations from the observed values. Then you square that. It is provided by this row that we have worked out here. So now the next step is to compute here from this formula. You will notice we need to get xi minus x bar squared. So we get the deviations of x from its mean. Now the mean of x is going to be given by the total sum of x divided by 19, and you get it's 55.57, which is the same as 5512.6. So you get the deviations, and these are shown here. So you will get this 27.95 minus 5512.6, and then you square, you get that. Then 31.3 minus the mean, this one here, 55.12.6, and you square, that's what you get. This minus the mean, you subtract 55.12.6, and you get this. So you repeat that all the way down, and then when you sum those values, the sum of those values gives you the sum of x minus x bar squared, which is this one here. So that's how you get that value. And now we have gotten all the values of that we require to input to compute the standard error. And so now we can compute the standard error. Substituting all these values in this formula here, okay, we get this result here. And the answer, the standard error, is 0.0023. So that is the standard error. Now we can compute, having computed the standard error, and we have got the t-value, we can now compute the confidence interval. And the 95% confidence interval is simply going to be given by B1, which is negative 0.0013, which we computed, times the t-value, plus or minus the t-value, times the standard error of B1. So now if you multiply this, what you get, then separate them. So you get negative 0.0013 minus 0.0049, you will get this result. And negative 0.0013 plus 0.00049, you get this result. So your lower limit is this one, and your upper limit is this. So graphically, this is what we have. Graphically, this is what we have. Your 95% confidence interval is going to be equal to this value. And so the lower limit, as we have seen earlier, this is what you have. Now, if we present it graphically, you have got the lower limit here. This is the lower limit and this is the upper limit. And now we can check, is 0 inside this? You will notice that 0 is not here. Actually, if I were to put 0, I would put 0 somewhere here. Indeed, 0 is somewhere there. And so 0 is outside this confidence interval. It is outside these two. It's not in between here. And therefore, what we conclude, because 0 is outside the interval, we conclude that the slope is going to be statistically significant, meaning that GDP is useful in predicting the 3-month TB rates. So as long as 0 is not in the interval, then the slope is going to be significant. Let's now consider how to compute the confidence interval for the constant. The 95% confidence interval for the constant is going to be given by this formula. You remember the way we calculated this, okay? So the t-value, this one, is going to be obtained from the table as we illustrated earlier. B0 is the value we obtained when we computed the estimate for the constant. And now the standard error is going to be computed using this formula. We go to our data. This is the data that we have, and this is the formula that we have. Remember, we have to compute the standard error of the residuals. So first of all, we compute the standard error of the residuals, which is the sum of yi minus y hat squared over 2. This one we had already computed. In the case of the slope, we found this one to be equal to 55.73. N minus 2 is 19 minus 2, which is 17. So we get S is going to be equal to 1.81. So now we need to compute to get the value for x squared and this other term here. So for x squared, this is the result you have. Square 2795.6, you get this value. Square 3131.3, you get this value. Square 3259.2, you get this value, and so on. So you can calculate all these values down, down, down. You can do calculate, and this one gives you the sum of the squared values of x, which when you calculate, this is the result that you get. Then the next thing we need is the sum of xi minus x bar squared. And this one we had already computed it earlier. Remember, this is equal to 5512.6. So you take 27.95 minus the mean, which is 5512.6 squared. So you can go to the previous slide on the slope. That's how we had gotten this one there. And this result, when you sum, this is the value you get, and it is the one that we have here. And now we can now substitute our values in the formula to compute the standard error of this constant, which gives us 1.35. Having done that, we can go ahead and compute the confidence interval. And the confidence interval for your slope is, for the 95% confidence interval, is going to be given by this, and then you substitute this one, and this is going to be 2.11, and this is going to be 1.35. This is what we computed when we estimated. So simplifying here and then separating the signs, this is what you get. So this one here is 14.15. You subtract 4.2. Okay. And this one here is 14.15. You add 4.2. Add 4.2. Okay, so that is how you get the upper limit and the lower limit. So now, from our result, we have seen that the 95% confidence interval for the constant has a lower limit of 9.95 and an upper limit of 18.35. So now we can represent this one graphically, and we have the lower limit and the upper limit. So this is the lower limit and the upper limit. Now if we look at this, 0 is actually going to be on the lower side. It's down here. So 0 is outside that confidence interval. And because 0 is outside this confidence interval, then it means that the constant is significant. So our conclusion is that the constant is significant, and therefore we need the constant in this model to be able to predict the TB rate. So that's it. That's how we compute the confidence intervals for the constant and also for the slope. In our next discussion, we will be looking at how now we test the significance of the whole model, the statistical significance of the whole model. Till then, cheers.